So I'd like to thank all the organizers, as everybody else. It's really a great format to be part of a school like this. When Eran invited me a while ago and asked me if you're going to commit for 5 weeks to stay here, you scratch your head. So it's really hard to commit. And I think this is one of the conditions to organize a school like this. But turns out that you can stay here. If you have some activity, you can leave and then you can come back. So it's much easier and much nicer than I thought initially. And the place is great. So I live in LA, which is close by, but this place is very different from LA, much quieter. The mountains are very close, ocean. So it's really great time. So thanks a lot, both for the scientific part, 1 or 2 talks a day, and then nice discussions. Was really great. So I'm a theoretician also, as the majority, but what we do, we model excited state dynamics. So people like Victor, they make some measurements, time-resolved laser experiments, for example, and we model those experiments. And we work on all sorts of materials, and I'll focus on 3 types of quantum dots that we study, which is traditional semiconducting quantum dots, like cadmium selenide, for example, metallic clusters, plasmonic clusters, and then recently perovskite quantum dots, which are also semiconducting, but their properties are quite unusual compared to the traditional semiconducting quantum dots. A few slides on the methodology that we use. So what we do, we combine, we need to describe evolution of electronic subsystem and vibrations. The electronic part we do by real-time TD-DFT, so we solve time-dependent Schrödinger equation in the DFT representation, time-dependent Kohn-Sham equations. And then for the evolution of the ions, we use molecular dynamics. But because we have to include transitions between different electronic states that can give you different forces on the atoms, and we need to include this coupling between electrons and phonons, and also electron-electron couplings, this now becomes non-adiabatic molecular dynamics, meaning that you are going beyond Born-Oppenheimer approximation. So it's a combination of those 2 approaches. And 10 years ago now, I had a very great postdoc who wrote a code, and now he's a tenured faculty already in Buffalo. So there's software that he develops, continues to develop, that we use and other people across the globe use. And he runs an annual summer school that students can use and learn the software. On the methodology part, so I come more from the non-adiabatic molecular dynamics community, not from the DFT part, from the chemistry side. So there are several fundamental questions that we try to address. So this is a mixed quantum classical approach, but it's not QMMM in the sense that you need electronic structure for fixed positions. We need to solve time-dependent Schrödinger equation and time-dependent like Newton's equation. And the question is how you couple dynamics of electrons of quantum subsystem and dynamics of a classical subsystem. And turns out there's no unique way. And if you try to think of this at the fundamental level, you can get to the point where you try to define, so you can try to combine commutator for the quantum subsystem and the Poisson bracket for the classical subsystem, and see if you can design some fundamental methods based on this kind of approach. So there's one big question, how you quantum and classical dynamics, not just static structure, but dynamics. And second set of questions, because we treat ions vibrations classically, we're missing some effects. So the most obvious one would be things like zero-point energy and tunneling, which turns out are important even perovskites. Everywhere you have hydrogen atoms, ligands, everywhere you have hydrogen atoms, you have some quantum effects, and those quantum effects can influence electronic structure. But also, there are more subtle quantum effects which have to do with the quantum dynamics, such as loss of coherence. So if you have a 2-level system, for example, coupled to a quantum bath of harmonic oscillators or any quantum bath, it influences transitions in this 2-level system a lot, and there's a so-called quantum Zeno effect where if you make a measurement on your quantum subsystem all the time, it's never going to make a transition. But if you treat your bath classically, you totally miss this effect. So you have to include quantum semi-classical corrections for this effect and other things. So what we also put a lot of effort into is implementing what we do with the ab initio DFT codes, and most recently we are using machine learning, as probably many people. It's a service to my students actually, because they all want to do some kind of machine learning and put it on their resume to get a job in Google. So our goal is, so we need machine learning forces, which by now is standard, but you can have more advanced versions, local versus global descriptors and so on. We also now have models of electronic Hamiltonian, so there's DFT, and then you can train a machine learning model of electronic Hamiltonian to ab initio DFT, and then we have some models of the non-adiabatic electron-phonon coupling, of electronic coupling, and so on. I'll briefly cover all those three topics, and then we also had a collaboration on modeling transport, although this is not really my work, it's a collaboration work, but if I have time, I'll show a few slides, which is kind of like what Sasha Efras talked about, but some interesting effects where you have tails. Sasha's lines were straight lines, but then you have tails in mobility, and you have some more advanced things to consider, like correlation and disorder. Okay, so quantum dot was the idea, going back to Sasha's work in the 80s, that you quantize energy levels of a semiconductor, and then you have particle-in-the-box description, and then you have properties that are very much like atomic properties. And this basically started the whole field of nanotechnology. We came into this field from the solar energy community, something that Viktor Klimov did to talk about Auger processes and how can you use extra energy that you have on the blue set of the solar spectrum to create more than one electron-hole pair. And we started to do our simulations, and what we learned step by step is that the properties of quantum dots are much more complicated than simple particle-in-the-box predicts, because this is a very good model for optical properties, but dynamics is influenced by many more things. So it's a much richer type of system than initially you would guess. So for example, if you look at this model, right, you would assume that if you make your dot smaller and smaller, you're going to open up energy gaps. And if you open up energy gaps, your losses to heat are going to slow down because these are heavy materials. And then heavy materials have low frequency vibrations. And then you have to make a transition across a fairly large electronic gap, you have to excite many phonons. So it has to be a multi-phonon process that's not very efficient. So if you reduce the quantum dot size, you should have slower relaxation. But in those days, this is experience from Viktor, what he saw is the opposite. First of all, the timescales were pretty fast. And second, the relaxation was actually slower faster for smaller dots. So smaller dots, larger gaps, but the electron phonon relaxation, energy losses to heat are faster. And this is all because the effective mass model gives you some envelope function, gives you optical selection rules, SPD type states, etc. But there are many, many individual states under each envelope function. And this is something that Eran sees also in his calculations on larger dots. But even in small dots like this one, 100 atoms, you have thousands of states. And if you look at any kind of dynamics, except for very special states right at the bottom, at the edge of the, near the band gap, you have huge densities of states, and those huge densities of states make your system behave more like bulk than an atom from the point of view of dynamics, because you have many, many states, dark states, that participate in the dynamics. And there's another feature of nanoscale materials, including quantum dots, is these Auger-like processes, which are pretty unique compared to bulk semiconductors or molecules, because in nanoscale materials, you have two things that are happening together. You have high densities of states, like you have in bulk semiconductors, but also you have pretty strong electron-hole interactions, Auger processes, Coulomb interactions, like you have in molecules, because in bulk materials, you have screening and charges are far, but here they're close enough, but the densities of states are also high. And that's why when people saw this phonon bottleneck, the relaxation time that was very slow on the order of a nanosecond, they had to remove the hole, so you don't have energy exchange between electron and hole by this Auger Coulomb-like mechanism. So this is what I'm talking about. You have electron that's excited, and you have a hole. And for electron, you do see some energy gap between the lowest energy state and then the next state. In relaxation across this gap, if you have no hole, if you remove it from the core, that's what was done by Philip Guérin in this paper, then you can reach nanosecond relaxation. But if your hole is coupled to your electron, because hole has many, many states, what happens, the energy goes to the hole, and then hole relaxes by vibrational relaxation, and then you don't see the bottleneck and you lose energy to heat, and this limits efficiencies of many devices like solar cells and lasers and so What we also learned in collaboration with Todd Krause is that if you think of chemistry of quantum dots, really most of those materials are not stoichiometric. So you have to do something about the surface. And when you have perovskites, you can have lead, for example. If you have excess lead, it creates lots of trap states. If you talk about cadmium selenide, as I'm showing here, it's the opposite. You actually want to have metal on the surface, but not the non-metal. So what he saw in this experiment was that he would make a quantum dot, cadmium sulfide, with two precursors, and those two precursors, you can mix them in different ratios, or you can add them later. So he would make a quantum dot, and then he would see emission, which is the red line, and the red line has a peak which follows from the particle in the box model, but there's also this very broad feature that already shows up in a realistic system that you cannot predict by a particle in the box model. But what's even more interesting is that if he adds the precursor that has sulfur, he totally quenches luminescence. At least the main peak disappears, but this it comes from defects. This peak continues to appear. And then he can add cadmium on the surface, and he recovers luminescence. And he would put sulfur on the surface, and it's gone. So something chemistry is very important. And the explanation is quite simple, because when you have metal on the surface, which is good, metal rich, metals heal dangling bonds in a very efficient way because they have d electrons. They can make metallic bonding. It doesn't have to be directional. But when you have sulfur, sulfur has more limitations on how it can heal unsaturated chemical bonds. And sulfur on the surface creates many, many trap states across the band gap. But the metal on the surface creates trap states too, but they heal. They create a little subband. And there's still some substantial energy gap is maintained. And it's emission from the subband that is responsible for this feature that is seen in experiments. Back to Auger processes and now transport, right? So in this case, I'm discussing experiments with of Tim Lian at Emory, and I'm talking about transfer of charge from quantum dot to a molecule. So this molecule is designed such that the level of the molecule is actually below the conduction band edge of the quantum dot. And the surprising fact was that, so in chemistry, there is this famous Marcus theory that was developed back in the 50s, and then in the 80s, it was demonstrated, this inverted, so-called inverted Marcus regime, which was surprising, and then he got Nobel Prize when this was demonstrated experimentally. So what it's about, it's a very simple model that's used to talk about transport or charge transfer in an incoherent regime. You have initial state, and then you have final state, and you have barrier that you have to cross. So if your final state drops in energy, the barrier becomes smaller and smaller. And at some point, there's no barrier, and this is when the rate is the highest. But if your energy of the final state is too low, you start crossing on the opposite end, and then the barrier shows up, and then the rate decreases again. And this is the Marcus inverted regime. And Tim Lian was trying to observe this in this system where you have quantum dot and a molecule. And instead of getting the inverted regime, he got saturation. And so what is the explanation? Because this is no longer a molecule, but this is not bulk material either. It's a quantum dot where you have strong high density of states and strong interactions between charges. So what happens is that the energy actually is deposited into the hole. So you have electron that's going from the quantum dot to the molecule, but the energy is not going to vibration. So this Marcus model, assuming that the energy goes to vibration, doesn't really apply, because the energy goes to the hole, and then the hole has high density of states, and that relaxes very fast to the edge. So within maybe 3 picoseconds, you don't even know that the hole was ever excited because everything relaxes to the final state. But this intermediate mechanism, Auger-like process, basically governs transport in this case, governs charge transfer from the quantum dot to the molecule. Okay, so let me now talk about plasmonic particles, which is in chemistry. So first of all, right, they absorb light very well. And people are trying to use this for photovoltaic applications, solar cells, or photocatalysis. And one of the big questions is it just a very nice heat source, right? Because you absorb light, you convert it to heat, and then you do photochemistry, not by photochemistry, but by just local heating, or there's more than that. But first I'd like to show you a typical small cluster
So there are three kinds of states when you have a metallic cluster. There's a state that's localized in the bulk. Then there's a state that's localized on the surface. And then you have the state which you can call plasmon-like. And in plasmonic response, you have many orbitals of this type. You have a superposition of many states like that, and that creates a plasmonic band. And these states exist in other systems too, in semiconductor clusters too, but at those clusters, they happen at energies that are too high. That's not relevant. But what's important in this state, which is also important for transport, as I'll show you, is that it's very delocalized, and it does not couple to phonons very much. So you have this electronic state, many of them, at sufficiently high energy. For metallic particles, they're at the visible energy of plasmon resonance. And this state extends maybe a nanometer into vacuum. So the barrier that Sasha was describing actually is not such a bad barrier because your state is delocalized a lot into the barrier. And because it's localized away from the core, electron vibrational coupling is very weak. So this red peak is very low. So the relaxation, losses energy to heat are also pretty slow. So this is collaboration with a group in Singapore. What they do in this case, they put gold and MOS2 together, and they can simultaneously measure the rate of charge transfer from photoexciting gold an electron goes to MOS2. And they could do spatial resolution, and when they do spatial resolution, they can also determine the distance between gold and MOS2. Because the surface is rough, so and MOS2 is flat, you can have variation in the distance. And then they measure rate as a function of distance, and they see this dependence that would be very weak. If you had vacuum between gold and MOS2, it would decay very fast. But this fast decay shows up only at the distance of 8 angstroms or so, almost 1 nanometer. And below that, decay is very slow. And this is exactly in our explanation for this reason that you have plasmon-like states that have extension pretty far into the vacuum. And those states facilitate charge transport that is much more efficient than you would expect if you just assume you have vacuum there. So now a question about photocatalysis or lifetime of states in plasmonic systems, and in general in nanoscale systems, you really have to sample configurations. So what you learn if you do just one configuration, some optimized structure, may not represent reality, what happens at room temperature and on longer time scales. So in this case, we developed a machine learning force field. And so this is a real system that people studied experimentally, where you have platinum cluster on the surface, and it could be used for plasmonic applications, could be used for photocatalysis. And we talk about charge transport between the two materials, and then the lifetime of the excited state in the metallic cluster. So what we see on the time scale of maybe 100 picoseconds or so, we have this oscillation. There's a structural evolution of the edge, or in this case, apex of the quantum dot, that changes the electronic properties. And the lifetime of the special state that's localized when you have the top atom detached from the rest of the pyramid becomes longer. And the difference is maybe just a factor of 3, but this could be quite important for chemistry, because when you have a bond, vibration of a bond is maybe 100 femtoseconds, and when you need to break this bond, if you have an excited state that lives for 600 versus 200 femtoseconds, it can matter. But so I think this is another general feature of many nanoscale materials. You have pretty slow fluctuations that you have to capture, and when you have fluctuations, changes in the geometry, your electronic properties change, transport changes, and you have to sample all this to get a representative picture of what's going on. Another question is now charge transport between between semiconducting metallic particle. And the question here was that if you excite, so traditional picture is that you excite a plasmon, and then plasmon breaks into electron hole pairs, and then electron would transfer to a semiconductor, for example. And the question I've always had is that how come they don't just relax vibrationally, because metallic particles are pretty large in experiments, they don't have any energy gap, everything should go to heat very fast. but people see photovoltaic effect when you put a metallic particle on a semiconductor. And what we saw in this paper is that if essentially have special states, interfacial states, you have charge transfer excitation. So when you photoexcite your metallic particle at the plasma resonance frequency, you have an excited state that leaks into the semiconductor. So you already have charge transfer during photoexcitation. So you have charge transfer excited state. And so this was 2014, and 1 year later, Tim Lian actually showed this experimentally. And what he did in this case, he grew metallic particles on a semiconducting nanorod. So the connection was also very strong. You had very strong chemical coupling, chemical bonding between the metal and the semiconductor, and this creates the possibility of exciting charge-separated state. Subsequently, we looked at the same kind of systems on 2D materials, and 2D materials are different from cadmium selenide or from titanium dioxide because they don't have any unsaturated chemical bonds. The surfaces are perfectly happy chemically, and in this case, this interfacial interaction is much weaker. Because it's much weaker, the importance of this photoexcited charge-separated state is much less significant. So in terms of transport, you would expect different behavior when you don't chemically bind the two subsystems versus when you bind them, and this depends on the substrate. If you're using 2D substrate, it's going to behave differently from when you have a 3D substrate and a surface with unsaturated chemical bonds. And going back to the Auger processes, this is now a collaboration with people in engineering, which is an interesting experience by itself because the language is different. Everything is heat capacity, electron-phonon coupling is heat capacity, etc., which is quite interesting for me to learn. But what's also useful is that people think of devices, which is also very important. So in this case, the aim is to have a heat flow. So and the goal is to have heat diode, so you can have heat flow one way but not going the other way. So in this experiment, what they've done, they put metal film, and then they have semiconductor, and then now they also have another metal here, and they're able to conduct heat one way and not the other way. So what happens in this case is that you have a metallic system where you excite electrons, and these electrons scatter with electrons in the semiconductor. So the semiconductor is intrinsically doped. It has some electrons in the conduction band. And instead of charge transfer, you actually have energy transfer. You don't have charge transfer, but what you have scattering or Auger-like process of excited electrons in the metal with the doped electrons in the semiconductor. And this scattering creates transport. And then if you have another metal on the other side, they scatter with the second. They go into the second metal, scattering with the electrons in the second metal. And then that metal relaxes, the electrons in the other metal relaxes to the ground state, and you cannot go back because you're already in the band gap in terms of energy. So Auger processes are very important for transport in these systems, not as well. So now I'll talk a little bit about perovskites, which is a very interesting material because it combines features of organic matter, inorganic matter, and even liquids to some extent. Of course, the motivation is that they're very efficient. You have very bright luminescence in quantum dots. For solar cells, you have very high efficiency, but the physics of the material is also very interesting. So what's the material? You have inorganic lattice, lead iodide, for example, and this inorganic lattice creates a continuous channel for transport. So that's why they conduct very well compared to organic, for example, materials. But at the same time, you have a pretty big space here, which you fill either with the small organic molecule or large inorganic cation. And this small organic molecule can rotate. It has a dipole moment, an even charge distribution. So you can think of it as a liquid because when you put a charge in this material, the dipole moment of the molecule can rotate, and then it can screen. So you can talk about solvation if you come from the liquids community. From the solid state physics, it's a polaron, but it's a very large polaron. So it's also very good for dissociating excitons because you have very large screening. You have whole electron, but they're all screened by the medium, by the material, and you separate charges very fast. But if you can find them, is it 1 or 5? Oh, okay. When you can find them, you have efficient emission. So the main feature of this material, why they're efficient, is that defects are not bad. And when we first looked at the material, we saw that when you have a trap state, so we looked at two types of defects that are most common. You have this halide that can diffuse, and if it diffuses, you have extra halide interstitial, which is this example, or vacancy, which is missing halide. So for interstitial, you have a trap state, but when the electron is, when the hole is trapped in this trap state, it does not recombine with the hole, because one reason is that this material has a very sparse lattice, inorganic lattice, and the trapped charge does not couple with the other charge. So the overlap of the wave functions is very small because the lattice is very wide and you have lots of space in the middle. So the trap states that are created are decoupled from the band states. But what we discovered also is that these trap states fluctuate a lot. So this is a soft material, so it's almost like organic material. And energy level of the trap state fluctuates so much that even if you think of it as a deep trap, at some point in time, it can become a shallow trap. So charges that are trapped in a normal semiconductor, they would stay in the trap state forever and then just disappear. In this case, they can escape back to the band. So if you have a 0.5 eV trap state in the band, it can fluctuate back to the band edge and escape to the band. And this is something that people don't see in inorganic semiconductors. So in that sense, I think all defects, or most defects in perovskites are shallow defects because there's always a fluctuation that brings it to a shallow state. Now the chemical part, so now it's the missing iodine. You have vacancy. So vacancy by itself does not create a trap state. But if you start putting charges through the device, charges can be trapped. And if you trap a charge, you create new species. So what happens, if you remove an iodine, you have two leads that are left out. And if you put an electron between them, you have lead to plus and negative charge in the middle. If you put the charge, it binds those two leads together. So you make a new chemical bond. And then when you make a new chemical bond inside this material around the defect, you create several mid-gap states. So again, something that's not going to happen in lead selenide, cadmium sulfide, because they're much more rigid. And here you have soft material that can create new chemical species inside. So you have photochemistry basically in this material. And this can also happen when defects diffuse. So you have vacancy creates no mid-gap state, but then vacancy diffuses to new location. And when it's diffusing, the mid-gap state shows up, and then this influences lifetime. Also, same thing can happen without charge, without diffusion, just simple fluctuation, but on a very slow time scale. So again, we developed a machine learning force field. What we see is that there's a very slow, some acoustic mode with a period of 50 picoseconds, very low frequency. And this mode brings those two LEDs together. When they come together, they make LED dimer, and they create many states, up to 3 mid-gap states that show up in the gap. But luckily, this happens transiently, so it doesn't really, even though you have a trap state that's 1 eV deep, it does not influence the performance. Because I only have maybe 1 minute, I want to mention briefly models of transport. So we had the collaboration with theorists that are doing hardcore pen and paper theory. So there's a standard effective transport level model, which says that when you have disordered medium and transport is by hopping, you have a distribution of trap states or energy levels that's usually assumed to be Gaussian. And then there's a thermal activation when your charge escapes, but usually it escapes and then it comes back. But if it escapes high enough, there are levels close by such that the probability that the charge that's high enough at this transport level energy is going to hop to a different site instead of being trapped again. So this is the basic idea of this effective transport level model. You have to go high enough, escape high enough to this effective level energy that you can have support transport versus trapping again. And simple descriptions like that, they give you straight lines. So let's see. So I'm comparing here Monte Carlo simulations versus a model, and here is the model, simple model, and this is the advanced model that my collaborators developed. So what happens here is that I'm plotting mobility versus applied field, and you have straight lines, but then you have tails. So in this example, when the field is very weak, you have a decay in the transport, but the decay is too fast if you have a simple model. So what happened in this paper, we showed that to be able to describe mobility at the low end, at low applied fields, you have to build in correlations. So basically you have an electron that has to detrap, and then you have another electron that's going to move. So if you include correlation between those two electrons, because one electron detraps and then it pushes the other one away, you can describe the mobility at low applied field limit that doesn't decay straight down. It has this saturation at the, it has lower, you have more efficient mobility because of the correlation. And then the other one, it's the same kind of model. Now I'm talking about so-called time of flight experiments, where you have material, you create charges, and charges move, and you collect them at an interface. And what's plotted here is the fraction of charges that remain inside the material, and this is current. So first you have a big wavefront that hits, and then current is continuous, and then eventually when all the main number of all the charges, the biggest number of charges escape, then you still have current remaining, you have a tail, but it's decaying because the mobile charges escaped, and you have charges that are left in the trapped state. And what happens again, you have this very weak tail that that lasts for a long time. If you have a simple model, standard model, your decay, your tail of decay is very sharp. But if you introduce disorder, not just disorder in the energy levels, which is a standard model, but also disorder in the coupling between levels, then you can have much better description of this tail. So weak mobility, you have to advance the models of the type that Sasha Effers talked about to include correlations or some disorder, and then you can describe finer effects. And this is the end. So we model excited state dynamics in various types of quantum dots. We look at interfaces of quantum dots with quantum dots or with other materials, which give us some idea of the transport between them, charge transfer, energy transfer. So chemistry is important. Also, in nanoscale materials, you have this Auger process, charge-charge scattering, which also plays important roles in transport. Plasmonic particles have these states that delocalize very far, and that is important not just to create plasmon resonance that absorb light, but also to facilitate transport. You have 1 nanometer gaps that could still be, you can still have efficient transport across those gaps. And yeah, perovskites are very interesting materials. They combine properties of inorganic matter and then organic matter and liquids, rich physics, and you can have finer effects in disordered media for transport. Anyways, thank you so much.
Uri.
Thank you very much, Oleg. I want to ask about this, the semiconductor metal hybrids with a PICT mechanism. So kind of a comment that usually for the photocatalysis, we need to excite the semiconductor and then get the electron to the metal.
Not this one.
Yeah, not this one, right. But then, yeah, the idea there that you can excite the metal and still get hot electron into the semiconductor.
Right.
Actually, you have to compete with very fast relaxation and back transfer to the metal.
Right.
So we saw that with this very elegant mechanism, but you have to extract that electron within like 100 to 200 femtosecond to avoid the back transfer. So the first question is, have you looked at this back transfer process also, how fast it is? One. Second, in relation to that is this system where you had, I think it was MOS2 with, yeah, that one, how fast is the transfer from the semiconductor to the metal?
Yes,
well?
So in the simulation, because we have limited size of the semiconductor, it bounces back. So electron goes in and then it reflects from the other side of the semiconductor finite size. But I think in reality, it just delocalizes because you have a large number of states. You can even call it entropy. Once you inject in the semiconductor, you have so many states in the semiconductor, there's no reason why it should come back. Energy drives it back, but you have many states where they can continue to move. So in the simulation, it comes back pretty fast.
But also experimentally, it goes back very fast. In the resonant case, when you have this resonance, which is needed for the PICT, what we saw is that then you have the back transfer, which for the relaxed electron. I mean, you have like, I guess, 100 to 200 femtoseconds to extract that electron from the semiconductor side to harvest this. Because, yeah, this is nice. You get, you can absorb into the plasmon in the near IR and still get an electron out somehow. Yeah,
you have to have some bias so that it moves
yeah,
in the opposite,
exactly.
away from
and do it fast. Yeah,
do it fast, yeah.
Oleg, you can clearly remember that when perovskites started used for solar cell, one explanation was that defect doesn't create level inside the energy gap. It looked like inconsistent with your discussion. Can you comment on that, please?
Yeah, so defects do create shallow traps even if you do optimize geometry compared to other semiconductors.
So the paper was wrong, huh?
No, they're not wrong, yeah. But there's on top of that, you have large fluctuations. So I think lead is special because it has very strong spin-order coupling, and there's some kind of band inversion. I think topological insulators also have lead, and I think CBM, HOMO-LUMO, they switch. So there's some kind of special electronic structure of lead that makes bands different from when you have lighter elements, which make trap states close to the band edges. So this is still true. It's still true, but I'm saying on top of that, you have very large fluctuations because even if the trap state is, so it has to be within KT for the charges to escape. But 0.1 eV, it's already more than KT, and you definitely have trap states that are 0.1 eV inside, but they fluctuate, yeah.
Thank you.
I want to follow on this maybe. So you've shown that these perovskites, we know, are quite soft. They give rise to these huge fluctuations. And also they have trap states that actually can go into the gap. How come they do so well in various light harvesting applications in transport? What's your take on this?
Yeah, so I think trapping is transient. You can get charges that are trapped, but at the same time, they can be detrapped pretty fast because of the fluctuations. Thermal fluctuations, you have thermally activated detrapping. That's important. Also, I should mention that, for example, if you have this dimer defect here, it cannot happen on the surface because you need to have two leads between which you're missing iodine, but on the surface you only have one lead. So in quantum dots that blink, traditional quantum dots, they blink because charges are trapped on the surface and create trap states. So this mechanism for this particular defect, which is the most common defect, it's not going to happen. So this actually helps quantum dots to emit better because you don't have charge trapping on the surface.
I really like your explanation of the reason that there is no Marcos inverted region for quantum dots. And if I understand correctly, it has to do with the density of states in the valence band, right?
Right.
That is very high. So I was wondering what would happen if instead of having photon-induced electron transfer, you have photon-induced Hall transfer.
But I'd say it has to do with the fact that you have an Auger process.
Which has two conditions, yeah.
Yes, but not just the density of states.
High density of states and strong
Coulomb right, but
fast
I mean,
Auger.
you can also have Auger in that case, but the density of states, if I understand correctly, in the conductance bands is not that high, right?
Yeah, so yeah, usually effective mass of the hole is much heavier. Yeah, so the density of states is higher. For perovskites, for these materials too. So usually Auger energy exchange goes from electron to hole because when you photoexcite, your energy mostly goes to electron. The one that has lower density of states, that's where you put more energy in. So I think this is more relevant when you have energy in the electron. And
so do you expect Marcos inverted region in that case or not?
For the when you have hole injection, so the still Auger processes will still be important. Maybe not actually, because you can still have that.
I think it was shown for both. Maybe Paul later on. Tim showed it first, I think, for the electron, right? And then Paul had a postdoc working with him showing the same physics for the hole too. Yeah. It's just the Auger and the scales is very fast. It's competing with the electron or hole transfer. And in molecules, we don't think about it this way because we never have charges on the surface or excite another exciton in a molecule. Very different regime. So.
Yeah, if you think of excited states not as electrons and holes, but excitons, basically have many excited states. And then your Marcos model can still work, but you have to include excitation of the hole of the other charge in addition to that. Yeah. If you diagonalize all the electron interactions out, you still have adiabatic electronic states and vibrations only, and then you can use Marcos model.
Sasha wants to say something.
I would like to add, in bulk material, second scattering mechanism is known like inelastic scattering of electrons with hole, when kinetic energy of electron transfer to hole.
Oh.
So you mentioned about perovskite also the polarons or the charge salvation. And I mean, I can imagine this in bulk, but can you comment on what happens when you go to nanocrystals? What happens with polarons when you go to nanocrystals?
Right, so I think polarons are very large. I think they're maybe even larger than excitons. So probably when you have a crystal where you see a confinement effect in terms of spectroscopy, you're already confining your polarons as well. So you still have polarons, but there's less screening because there's a less, you have a smaller polaron. So I think it still should exist. I'm not sure about surface because this happens not just because of rotation of the organic molecule. If you have inorganic cation, you also have pretty large polarons. And surface maybe creates extra flexibility. So that can also have an effect. But basically you reduce the size of the polaron, which increases Coulomb interactions. And that's why they emit well, actually, yeah.
In principle, the exciton, the competing energy scales are the exciton binding energy, which increases with decreasing sizes, and the reorganization energy, which has the same trend. So as you decrease the size of your particle, you're moving more and more into the molecular regime, which has stronger electron-hole coupling and also stronger coupling to the phonons, and so more significant polaron shifts.
Yeah, if you have defects, you create local, you can have small polaron basically. Lead dimer, it's a small polaron, yeah. Like you have in TiO2.
I'm an outsider in this business, but I have a question on the methodology that you use, because I had the impression you go beyond the Born-Oppenheimer approximation. Could you say a few words, because it went very quickly for me, how you actually do this?
So in the simplest way, we run a molecular dynamics trajectory, and then we compute non-adiabatic coupling, which is beyond Born-Oppenheimer, which is how, this depends on how electronic wave function depends on nuclear coordinate, which is a form of electron-phonon coupling. But, and this coupling couples electronic states due to phonon motion, and then there's a probability of transition. And there are different ways how you actually do the simulation, but yeah, you solve time and pattern Chernigov equation with this non-adiabatic coupling. Yeah, that gives you probability. And the most useful method that people use is surface hopping, but the simplest one is Ehrenfest. It's a mean field method where you have average, quantum mechanical average couples to classical variable in the spirit of Ehrenfest theorem, but it has some problems. Yeah. So it's molecular dynamics with electronic transitions, maybe that's another way to call it. Yeah.
Thanks. Mm-hmm. So just in terms of the dynamics, this is a nightmare for a theorist because you're basically solving a particle that has multiple, you've seen how many excitonic states, and they're all coupled. And you also have to simulate the phonons and the vibrations, and in the perovskite materials, those are nonlinear, and harmonicities plays a role. So it's a nightmare to solve the dynamics. Oleg has made significant progress, I'd say, over the last 20 years since you started working on particles and developing first principle calculations. You're still limited to small systems, and maybe in the future you can go to a little bit bigger and see size effects and so forth. Yeah, basically chemists have been doing this from the 60s for gas phase reactions. But then condensed matter came in, yeah, and I made some contributions to make it, with extra approximations to make it more efficient, I guess, and combined with real-time PDDFT, which actually is a pretty unique methodology, I would say. And now we're trying to do machine learning to make it bigger, yeah. All right, so I think we're right on time. It's time to take a break. We have 2 more lectures in the afternoon, and let's thank all the speakers today first, and then you'll announce something.